let's look at something called the graphical method. And in the graphical method, what we're going to be doing is something that's somewhat similar to what we did in the numerical method. We're going to be looking at values close to C and seeing what, so X values close to C, and then we're going to see if there's a pattern. Do the Y values seem to be approaching any particular value? So let's look at the following function. And I'm going to back out just a little bit. Here's a function that is graphed. It's kind of an unusual looking function, but it is a function that passes the vertical line test. So in this function, can we determine what the values of these limits are? The limit of f of x as x approaches negative 4. Now, I didn't say this, but this xy plane is marked off so that the grid, the squares in the grid, have size 1 by 1. So, for instance, there's x equals 1, there's x equals 2, x equals 3, y equals 1, 2, 3. Here's negative 1. There's negative 1 on the x, negative 2 on the x. Alright, so the limit of this function as x approaches negative 4. So x equals negative 4 would be right here. So the question is this: as we travel along this graph and let x get close to 4, do the y values seem to be approaching anything? Well, it looks like that the y values are maybe approaching negative 2. The y values can be made as close to negative 2 as we want by choosing x sufficiently close to negative 4. Here the y value isn't all that close to negative 2, but if we move on down here closer to negative 1, the y value is quite a bit closer to negative 2. Alright, what about the limit of f of x as x approaches negative 1? That's right here. You see the circle here. You remember what that circle means. That means that that point has been removed. So there's a, this function is not defined at negative 1. So can we find the limit of f of x as x approaches negative 1? Well, remember that what we're doing is we're traveling along the graph and we're letting x get closer to negative 1 without necessarily going all the way to negative 1. And in fact, we don't want to go all the way to negative 1. But as the x values get closer to negative 1, do the y values look like they're headed toward a particular value? I would say they look like they're headed toward negative 3. Now, does the function ever take on the value negative 3? It doesn't look like it does, but that's okay. The x never takes on the value negative 1, but we can let x get awfully close to negative 1, and by doing so we can make y very close to negative 3. In fact, as close as we want by choosing x sufficiently close to negative 1. Alright, let's go on to the next one. Here we look at the limit of f of x as x approaches 2. So that's right here. So as we let x approach 2, what's happening to the y values? Well, you might remember in that example where we looked at numerically, we let x approach 1, I think it was. Yes, we let x approach 1 from each side, from the right side and from the left side, so values bigger than 1 and values smaller than 1. We want to do the same thing here. As x approaches 2 from the left side, values of x that are smaller than 2, it looks like maybe the y values are headed toward 4. But if we let, I'm sorry, negative 4. So I'm going to write that down with a question mark. And then when we restrict ourselves to values of x that are always bigger than 2, well, it looks like the y values are headed toward 2 as x approaches 2. So from one side it looks like the limit is 4, from the other side it looks like the limit is 2. What do we do in a case like that? Well, since there's no agreement here, we say that the limit does not exist. There has to be agreement between the left side and the right side. All right, finally we've got one more example, and that's the limit of f of x as x approaches 5. So that's right here. Here's x equals 5. So look what's going on here. The graph is going along, then all of a sudden there's a hole here, and then this point is not here, but instead we have a point down here. The function is defined at negative 5. What we would say is that f of negative 5 is 2, right? When the x-coordinate, I'm sorry, that should be positive 5. When the x-coordinate is positive 5, the y-coordinate is 2. So f of positive 5 is negative 2. I think I've got it right finally this time. Sorry about that. If we let x take on the value 5, we're not looking at this point, we're looking at this point. F of 5 is negative 2. But what about the limit as x approaches 5 of this function? Well, if we were in an algebra class, we would probably be looking at a question like this one that we just answered. What is the value of f at x equals 5? But when we're looking at the limit, what we're looking for is a tendency. If we let x get closer and closer to 5 from each side, but without going all the way to 5, is there a value that the y values seem to be approaching? I hope you're thinking that it's 3. That this function, the y value of this function can be made as close to 3 as we want by choosing x sufficiently close to 5, but without picking 5. Let me say that again. The y value of this function can be made as close to positive 3 as we like by choosing x sufficiently close to 5, but not equal to 5. I think you can see that the closer x is to 5, the closer y is to 3. But now at x equals 3, y is equal to negative 2. But remember, part of the definition of limit is we don't care about what happens at x equals negative 5. If anything, at x equals positive 5. If anything, this point is really a distraction in determining what the limit is. If I were to, say, cover it up like that, then you can't really tell what's going on exactly at x equals 5. And that's okay, because we don't care what happens exactly at x equals 5. We're just looking for a tendency as x gets closer and closer to 5, but without going all the way to 5, do the y values settle down toward a particular value. So in this case, we say that the limit is 3.